Okay, so I would like to welcome you and the third meeting of the Artificial Intelligence Seminar in AGH University of Krakow. As you can see, we have decided to switch from Polish to English. And this presentation will be given by Jakub Adamczyk, who is a PhD candidate at AGH. And he will give a talk entitled Topological Descriptors in Graph Classification.
So, hello everyone. I'm a PhD candidate at AGH University of Krakow at the Faculty of Computer Science, and I wanted to give this talk about topological descriptors in graph classification because this is what my PhD concerns. So we have a lot of things here. We have graphs, graph classification, topological descriptors. So let's disentangle. And the first thing, why graphs? Why would we care about graphs? So the thing is, graphs are absolutely everywhere. Graphs are the most natural way to represent a lot of data around us. For example, traffic networks, travel networks in general, chemical molecules. We have social networks. We have graphs that we build ourselves, like knowledge graphs, where we connect some facts and relations between them. So graphs are absolutely crucial to understanding and representing a lot of data, and therefore we are probably interested in utilizing them to the fullest extent. So we have a lot of tasks on graphs, and those tasks are very natural to represent on graphs. For example, graph classification, where we want to classify the whole graph, where we have a single label for the whole graph. For example, this is absolutely dominant in computational chemistry, where we want to predict some function of the whole molecule. For example, is the molecule toxic or not, or how soluble it is in water. So there's a singular label for the whole graph. You can also have the node classification, where you classify nodes inside typically very large graphs. For example, node classification is very popular in social networks. For example, if you have a network of users, for example on Facebook, you want to classify whether a particular user will respond to an advertisement. So this is a classification of nodes, here users, inside a very large graph. You can also have link prediction, very related, because link prediction is also used for recommendation, predicting new links. For example, when Facebook recommends a new friend for you, it actually does the link prediction on the social network. You can also have community detection, again, very useful in analyzing social networks, detecting communities, clusters of nodes in large graphs. We have graph embedding, where you want to compress the graph into a finite dimensional vector. This is very useful in de novo drug design, where we want to do molecular similarity search, where we want to search for molecules that are similar functionally or structurally to some queries. And we also have graph generation. Graph generation is basically the holy grail of generative drug design, where we want to just have some drug and generate other drugs that are similar to it, but for example don't have so many side effects. So we have a lot of tasks on graphs, but I'm concerned here primarily about graph classification, where we want to do classification or regression on the whole graph. Especially because it's extremely important in bio and chemoinformatics in many, many different ways. For example, we often do molecular property prediction, where we want to predict, for example, is a molecule an HIV inhibitor? Is it soluble in water, in fat? Typically, in the drug design process, you have to solve this task of molecular property prediction like tens of times for different things. So we have a lot of those classification tasks there. We can also predict the properties of proteins in bioinformatics. For example, do two proteins bind together? This is extremely important also in drug design and related subjects. And we also have molecular similarity search, where we want to search for similar molecules. This typically, the searching is the first phase, and then classification of the results is the second phase. But to do classification, we also need to do vectorization typically, which is important for searching. And also this has many other different applications, because in many different ways we create a graph and from some data to represent it in graph form because it's useful due to some properties, and then do things on this graph. For example, in social network analysis, you may want to classify the type of the community. based on its connectivity structure. We also have very interesting papers about program code analysis. You're representing the program code as a graph. Also, in computer vision, we can represent, for example, scenes of objects as graphs and analyze what's on the image as a graph of objects. And also we have algorithmic reasoning, extremely interesting area, where we represent some tasks in terms of algorithms as graphs, and we want machine learning to automatically learn how to perform certain classical algorithms, but to learn them. For example, learn to sort things. So there are extremely interesting things using whole graphs. And okay, so we know why graphs, why graph classification. So how can we do this? So actually, every classification task, no matter the object, can be or does require indeed to do two things. Firstly, you need to vectorize your object. So you need to calculate a feature vector from the object. No matter if it's text, image, graph, anything. You first take an object, turn it into a vector, and then you can classify it. This is basically how every algorithm works. Because we can do this more or less automatically, but the process is the same. If you do manual feature engineering, you just calculate some features, get a feature vector. You can do this by using some embedding algorithm, which is typically less or more complicated way to just statically compute some features from the object. And those are, for example, graph kernels, molecular fingerprints. Those are algorithms for graphs. And we also have neural networks. Neural networks actually also do this exact thing. Because while neural networks do representation learning, so they learn to intelligently, more or less, learn those vectors, they do this just fully automated learning, but they automatically learn those vectors. They use this backpropagation scheme, etc. But what they do is they take an object, vectorize it, then put it into the multi-layer perceptron. So neural networks may seem different, but really what they do is feature extraction and then classification. So let's do a few basic definitions on graphs and descriptors. This will lead us to some very interesting methods how to use them in practice. So a graph is a combinatorial discrete structure. This is extremely important, and this is why graphs have been a huge challenge for machine learning. Because, naturally, there is no Euclidean structure to graphs. There is no xi, there is no distance metric, algebraic space. We basically can't do anything from linear algebra or analysis on graphs. And this is extremely problematic, because no notion of distance, no notion of metric renders all classical algorithms totally useless. We can't even do things like, I don't know, convolution or attention or anything like that on graphs. And also, this means that everything we do must be permutation invariant, because graphs don't care about order. Graph consists of an ordered set of vertices and an ordered set of edges. No matter what we do in machine learning on graphs, everything must take this into consideration. What we do cannot depend on the order of processing. And this actually has been a huge challenge for decades, because it's extremely hard to prove that something is permutation invariant, to make this work well, generalize well. And also we can use either those sets or adjacency matrix. That the problem is the same, but we have those two representations. And actually we have some notion of distance. And to introduce this, we need to talk about neighbors. So nodes are connected by an edge, and then they are neighbors. So you can see here on the right, we have this gray node here, and their neighbors. And those are so-called the direct neighbors. If two nodes are just connected by an edge, they are direct neighbors. And we can hop through those edges to walk through this graph. So a graph can be thought of as just a set of network of roads, and we just go through those edges, which are basically roads, through the graph. So we walk through them or hop through them. And one hop or direct neighborhood is the set of nodes directly connected to some other node. So you can see here on the right, so the direct neighborhood of this gray node is this set of red nodes directly connected to it. And we can also define k-hop neighborhood. This is also very, very useful in machine learning, where you define the neighborhood around the node, but it's not only the nodes directly connected to it, but also nodes connected to those directly connected nodes. So you just hop through those edges from the starting node k times, and where you go, this is the k-hop neighborhood. So this is basically the set of all nodes where shortest paths are at most k. Also, shortest paths will be pretty important in a while. The shortest paths are shortest path is the smallest number of hops, the smallest set of edges that we have to take between one node and the other node. You can see this here on this image on the right. Shortest path between y and z are those red edges. And this shortest path distance, where you hop through edges, is the only notion of distance that you have on graphs. This is not Euclidean, you don't have any xi, you can do many mathematical operations on them, but this is some notion of distance, the only notion of distance that we have, so we better use it well. And indeed, this will be very useful in a while. But nodes have one very crucial, very basic property. They have a degree. So degree of the node is equal to the number of its neighbors, or direct neighbors. So we take this set of neighbors, set is unordered, the size of the set is a degree of a node. So this is the simplest topological descriptor. So the thing that you came here for, right? Topological descriptors. So vertex describes the graph topology, so its structure. Structure and topology is the same of the graph. Vertex is, of course, very limited because only describes one hop neighborhood, so it's very, very local. But indeed, it describes this local structure. If a node has a very high degree, it means it has a lot of neighbors. If node has a very small number of neighbors, it has a small degree. So it definitely describes something. And this is permutation invariant because sets are unordered. So the size of the set, of course, is also permutation invariant. And it is the most commonly used descriptor because while it's very simple, it's also very useful. And it's very, very local. We will see more global descriptors in just a minute. And also, it should be noted that descriptors are not only topological. In fact, they are often not topological because in practice, graphs are always or almost always attributed. So you have some attributes, some features that are very inherent to your domain. For example, for molecular graphs, we have atom types or bond types. Because, well, you can't do chemistry without knowing what atoms you work on, right? So this basically forms the feature vectors for your nodes or vertices. Node and vertex is also the same. For your vertices and for your nodes. And those feature vectors, of course, are our choice. We can describe how to compute them. For example, in chemistry, we have very many different ways to describe an atom. But they come very naturally from a domain or are crafted by us. We can use those atomic elements, we can use bond types, we can use user features, for example, because we can build those graphs ourselves. We can build features for users, for example, their age, number of purchases, total money they spent so far. But we also can compute those features using other algorithms. There are, for example, extremely interesting papers from NLP which build the graphs of connected texts where node represents a text and features are embeddings from BERT algorithm. So those feature vectors for nodes can be very high dimensional. They can describe very complex semantics. But nevertheless, they come with nodes. We can use them. We typically use them very, very strongly in our algorithms. So those are not topological. So let's talk about those topological descriptors on the other hand, right? So topological descriptors describe the graph topology or its structure. They have many different names because they come from very different branches of science. They are also called graph properties, graph invariants, because they are permutation invariant, right? So they are graph invariants. We have graph descriptors, all the same. They typically come from graph theory, so pure mathematics. They can come from social networks, mathematical chemistry, many, many different fields. And also they have very confusing and overlapping names sometimes, so it's not particularly easy, but they can describe structure of nodes, structure of edges, structure of subgraphs in a graph, or they can indeed describe the whole graph at once. And some examples. We have vertex degree, which I have just talked about. So vertex degree describes a node, very local, very simple. For example, is edge a part of a triangle? I mean, real easy triangle, so you just have 3 nodes connected to each other, so this is a triangle. Is an edge part of a triangle? This is sometimes quite useful. Or, for example, you can have distribution of shortest paths lengths. So you, for example, can have a descriptor, which is not a single value, but rather a whole range of values. So you take a whole graph and you check the distribution of the shortest paths lengths. So, well, are shortest paths typically very long or very small, or are they normally distributed? This can tell you a lot about graph connectivity, especially for social networks. This is quite important. Or, for example, in chemistry, there's a notion of Wiener index by Harry Wiener. Wiener index is the sum of shortest paths lengths. So you calculate all shortest paths in a graph, all possible, and you just sum up their lengths, and this is the Wiener index. It's actually very well correlated with many physiochemical properties of a molecule, despite being very simple. So this is pretty useful. And how to do graph classification using those topological descriptors? The idea is as follows. Firstly, we compute those topological descriptors. We compute them for vertices, for edges, for the whole graph, whatever we want. It's our choice what we compute. Because, for example, we may have some domain knowledge, for example, in social networks, that some descriptors indeed work quite good. Then we concatenate those descriptors into a vector for the whole graph. So because you want the whole graph representation, right? You want a one feature vector for the whole graph, and then we classify it with any off-the-shelf machine learning algorithm, whatever it may be. And there's one problem with this, because this is the nice idea, but there's one problem, that in basically any classification algorithm, your feature vectors have to be of the same length. So you have the same dimensionality of features for all your objects. And here, there is a problem, because we need a feature for the whole graph. And for example, degree is separate for each vertex. So if we had 2 different graphs with different sizes, you would have the different number of descriptors, because there's a different number of nodes. So we need a constant size vectors with features aggregated for the whole graph. And this aggregation is exactly what we do. We need to aggregate vertex and edge descriptors into the whole graph descriptors. Actually, the Wiener index is a nice example, because the Wiener index is the sum of shortest paths lengths. So it creates a single float, or a single number, from the whole array of lengths of shortest paths. And there are many different aggregators. They are very, very simple usually. Sum, mean, minimum, maximum, standard deviation, or whole histograms. They are very simple statistical aggregators. For example, you can have a total sum of degrees, histogram of vertex degrees. You can have average path length, sum of paths lengths, etc. So you can indeed aggregate a single feature in many different ways, right? Because you can, for example, compute minimal degree and maximal degree, and those are 2 different features for the final whole graph representation. And once we compute all those features, we concatenate them with those aggregated features, and we have the feature vector for the whole graph. So this is the whole pipeline, how to do this. We have this input graph, which consists of 3 things. Adjacency matrix, which defines the graph topology. Node features and edge features. Node features and edge features are, for example, atom types, bond types. So, for example, in chemistry, it's very useful to compute the total number of atoms of each type, obviously. So this is, for example, this. The total number, for example, of aromatic bonds. This is also very useful, so this is here. And whole graph features are, for example, graph radius, Wiener index, etc. So things that are very naturally on the whole graph. Or we can have node and edge topological features which need to be aggregated somehow. Then we concatenate all of those things, and then we get the feature vector. This is actually very cheap to compute, typically. Very simple in code. So this representation is really very easy to create, and it's pretty powerful despite its simplicity. So the problem is how to select those descriptors. if we look at a few books, molecular descriptors for chemoinformatics. This is basically a huge brick of 1,000 pages, it's pretty huge. There is a lot of molecular descriptors. By the way, molecular descriptors are really just topological descriptors, but on graphs. Or there are some topological and feature descriptors there, but you get the idea. So another book, Handbook of Molecular Descriptors, also 1,000 pages. Also, there seems to be a lot of descriptors in chemistry. So let's see something much simpler. Network X and Network Kit, two libraries in Python. So we have tens of descriptors into those two libraries. And indeed, each of those descriptors can be aggregated in multiple ways, right? Because, for example, for each descriptor, we can calculate all of those statistical aggregators. So we have thousands upon thousands of different descriptors possible, available. We have their combinations, transformations. So how can we apply this in practice? So first practical example, local degree profile algorithm, or LDP. So local degree profile has been proposed in a paper by Kai and Wang, a simple yet effective baseline for non-attributed graph classification at ICML workshop. And this is a topological baseline for graph classification. So firstly, this is based only on graph topology. This does not use any attributes at all. Even if you have attributes, LDP does not use them. This is meant as a baseline. So when you do classification, for example, for a scientific paper or for work, you have to have baselines. You have to have simple algorithms that you compare to. Because if your super complicated, super costly neural network can't beat a simple baseline, it means that either you are doing something wrong, you have a bug, or a problem is really simple. So this is very important to have some simple baseline, and this is what LDP is for. And it's based solely on vertex degree histograms. So it does not use anything apart from vertex degrees. So it uses just the simplest topological descriptor available, just in a very smart way, because it gives really good results. In fact, it has been shown that this method, based only on vertex degrees, can beat very powerful, very costly graph neural networks. We will see in just a minute. So the algorithm is as follows. You compute 5 descriptors for nodes. So those are node descriptors. For each node, you compute its degree, which is quite obvious, and you compute statistics of neighbors' degrees. So you look not only at the node, but you look at its neighborhood, and for its neighbors, you calculate their degrees. And from degrees of the node neighbors, you compute their minimum, maximum, mean, and standard deviation. So this way, you very cheaply get information about two-hop neighborhood, about the node, its neighbors, and their neighbors. Because degrees of neighbors tell us something about their neighborhoods, right? So this is a two-hop neighborhood information, and computing this is extremely cheap because its computational complexity is basically equal to the number of edges, or proportional to the number of edges to be precise. So it's very cheap. You aggregate each of those features with a histogram. So you have a histogram of vertex degrees. You have a histogram of average degrees of neighbors. You have a histogram of minimal degrees of neighbors, etc. Right? So you just take those 5 features for each node, compute a histogram of each of 5 features, concatenate this into a huge vector, and classify this with SVM or random forest. Really, really simple idea. And original paper has 4 hyperparameters, uses SVM. It's more complicated than it actually needs to. Because in a paper by me and Dr. Wojciech, we showed that we can, in practice, remove all those hyperparameters. On average, they don't give you anything at all. You straight up can remove those hyperparameters, use 50 histogram bins, and don't care. And this really works in practice. On average, this setting, you just calculate histogram of vertex degrees with 50 bins, etc. Concatenate this. This has 250 features in total. You just classify this with random forest, which is additionally very simple to use, very simple to tune. You get really good results on average. If you see those results, those are model ranks on considered datasets. So the lower the rank, the better. So the best model is first, the worst model is second, etc. So the best possible rank is 1, where you have always the best model, and LDP, the penultimate column here, has 4th rank in general. So on average, on 9 datasets that we used, it was 4th. It means that it was better, for example, than GraphSage. GraphSage is a pretty popular graph neural network. It was better on average than DeepPool and ECC, which are extremely computationally intensive. In fact, ECC was not able to finish on all datasets because it was out of resources. So LDP, despite its simplicity, is very powerful. And remember, this does not use any attributes at all, even if they were available. So we have this last column, which I will talk about now, because this is the local topological profile, which follows basically the same idea, but was proposed by us and gave better results. So the idea from the same paper is as follows. We extend the LDP with 3 additional descriptors. So we compute additional descriptors, combine them with histograms in exactly the same way. But we thought that vertex degrees are not enough. We thought that we can cheaply and easily add more descriptors and get better results. So the idea is to select the descriptors that provide information about more global graph structure. Because there are some descriptors that are computed, for example, for an edge or for a node, that with this single number combine the knowledge about large parts of the graph. And especially if you compute the histogram of those features, you get a lot of information very cheaply. So those are those 3 additional descriptors. I will talk about them right now. They are all very cheap to compute. It's pretty important. So edge between the centrality is one of the so-called centralities on the graph. Centralities tell you how central, how important for the whole graph is the single node or edge. For example, on Twitter, the president of the United States it's typically has extremely high centrality because he's in the center, right? Everyone follows him. So nodes or edges with high centrality are in the heart of the network. They are typically used in social networks. And this is the edge feature. So edge between the centrality describes an edge, or precisely, it is computed as the fraction of shortest paths that go through a given edge. So we compute this for each edge, and we compute the histogram of this. And edge between the centrality will be high if there are bridges in the graph. Because a bridge, so the edge that connects 2 components of the graph, requires all shortest paths to go through this. If you want to go from the left to the right here, you have to go through this edge. So this edge, in a way, controls what happens in the graph. If you want to go from left to right, you have to go through this edge. So this controls the information flow for the graph. If this was the social network, indeed, people on the left talk to the people on the right only through this channel. And on the other hand, if there are no such edges, the histogram will show you mostly low EBC values. So this is pretty cheap to compute. In fact, you can compute this in pretty much linear time. For each edge, it aggregates the global information, because for each edge, you get information about all shortest paths. Histogram of this will be very informative. So this is the first descriptor. Second, Jakub index. Jakub index provides information about subgraphs, and it's computed as the overlap in neighborhoods of 2 nodes. So you take one node, second node, neighborhood of 1, neighborhood of second, and you calculate how much is the overlap between them. You compute the number of common nodes divided by the total size of those neighborhoods. Very, very simple to compute, very cheap. And this provides you the information about the connectivity of the graph. If the neighborhoods overlap very much, so this means that 2 nodes typically have a lot of neighbors in common, then it shows that the graph is very tightly connected. It has a lot of connections. It has typically very short paths between nodes. And if Jakub index is typically low, this means the graph is sparse, it's very long, there are not many connections there. So this is the second descriptor. And third one is the local degree score, which is a bit more complicated to understand. It's still cheap to compute. But the idea here is to, for each edge, provide information about global structure of communities in a graph, of nodes or node clusters. So this measures for each edge how important it is to keep the components of the graph connected. Where components are node clusters, like communities, tightly knit groups of friends, which are typically connected by very small number of edges between them in a graph. So local degree score will be high if in the graph there are visible communities. And in fact, it will be also very high if there are so-called hubs in a graph. Hub is an influential vertex with very, very high degree. Hubs are typically influencers, well-known politicians in the social networks. So they have very high degree, and they typically cluster people around them. So connections between those communities will typically have high local degree score. The formula is pretty complicated. I won't exactly go into details here, but shortly, it counts on average for a given edge. Does this connect on average very high degree vertices? So are two influencers on the ends of an edge. And when we add those three descriptors, the histogram of each of those three descriptors, actually we improved the average rank of our model from 4th to 2.6, and this gave us, on average, the best results on 9 datasets. What's more, in fact, we got state-of-the-art results on 5 out of 9 analyzed datasets, again, using very, very simple methods. This took basically a few seconds to compute those features. So it's extremely efficient. And those were social networks, where we got the state-of-the-art results. Because it turns out graph topology is absolutely not enough for molecular datasets. For molecules, you really need, at the very least, the atom types. If you don't have that, well, for molecules, the shape is not enough. I mean, it's pretty obvious, but this is numerical proof that this is true. So this is the LTP method. Just you add 3 more descriptors, you have 400 dimensions instead of 250, and this just works. So there are a few other examples, also from our faculty. So first example is from Nurip's workshop, a simple Bayesian algorithm for graph classification. This is, if I remember correctly, from 2018. And the second is from ICLR workshop from 2019, invariant embedding for graph classification. And indeed, those methods were also very, very good. So this shows that this area is really an active research area. Also, relation histogram, order histograms as network embedding tool by people from our faculty, also very recent. And in fact, we have 2 PhD theses in our faculty about this exact topic by Dr. Wojciech Czech and by Dr. Radosław Łazarz. This one very recently, very, very recent. So yeah, you can even do a PhD on topological descriptors for graph classification. So quite useful indeed. And now I have a short section on graph neural networks. How much time do we have?
20 minutes, about more or less.
Okay. Okay, so very, very short primer on graph neural networks, because I want to talk about them and how to combine them with topological descriptors. So graph neural networks, in their essence, the classical graph neural networks, work basically like convolutional networks, but you input graph instead of image. So you have an input, which is a graph. You do graph convolutions instead of regular convolutions. Convolution, convolution, convolution. Then you aggregate the information for the whole graph, just like with histograms, but in fact simpler. And you just do the MLP and softmax and classification. So the basic structure is exactly like like convolutional networks, but you need to define the convolution other way. So actually, input to graph neural networks does require manual feature engineering. This is pretty different than typical neural networks, where you just put the image and don't care. Here you pass the adjacency matrix, which defines the graph structure, and you also have this feature matrix for nodes. So you need to extract features for nodes yourself. And in fact, what features you input into graph neural network is pretty important. You can have great performance boost if you compute better features, especially, for example, for molecules. And adjacency matrix defines how to pass information in the graph. We will see that on the next slide. So yeah, to reiterate, you have graph structure, which is typically predetermined, and you have graph node features and optional edge features that you compute yourself. And graph neural networks work based on the notion of message passing. So for a graph, in each convolutional layer, you have a node. A node has a feature vector. When we start, those feature vectors are calculated by us. So we have those starting feature vectors. You extract like 5 or 10 features for each node. Then each node takes its vector and sends the vector to its neighbors. So it packs up a message, this vector, and sends the vector to its neighbors. So a node gets a vector from a vector from each of its neighbors, and then we take all those messages and we aggregate them. How we aggregate them, it depends on the network. The simplest way, you just compute the mean. So you can compute the average message from your neighbors, it's okay. And then you have the aggregated message from your neighbors. So basically each node talks to its neighbors and says, hey, I'm the node, this is what I know about myself. So they send this message, we aggregate those messages, and then the node thinks, okay, so this is what my neighbors tell me. Now I will update my own knowledge using this aggregated message. So we take the existing node vector, this message, and we update this. Again, this can be a simple mean or something more complicated. How you define this aggregation and update operations, this defines many different graph convolutions. But the idea is basically this. You pass messages between neighboring nodes, they send those messages, aggregate them, update the node representation, and do this for a few layers. Typically, also graph neural networks are very shallow, so you do this like 2 or 3 times and that's it. And then you aggregate the information from the whole graph using the readout function. Readout is just a fancy name for aggregating the node vectors. It's just the traditional name. So you have those node features stacked in rows, and in columns you have different features, which are of course computed automatically via backpropagation. And the simplest readout, which is also the most commonly used and it really works, is just to compute the average of each feature. You just compute the column-wise mean, or the column-wise max, or the column-wise sum. It's very simple. You can compute a few and concatenate them. There's no problem. You can compute all of those and just concatenate them into one large vector. But this is the idea. Compute the features for nodes, aggregate them, get the representation of the whole graph. Okay, I hope you understand. This is very similar to topological descriptors, just here this happens more or less automatically when you learn with neural network. So, how to combine this idea with topological descriptors? We actually have a few ways how to do this, and each time someone does this in a paper, it greatly improves the results. So really, you should do this. Because, for example, you can use those descriptors as just node features. You just compute topological descriptor for each node and you just treat it as any other feature. Just like atom types or anything else that you put into the network. You just calculate topological descriptors, add them as node features or edge features if your network uses that. This is also often called an encoding in this regard, like graph positional encoding, Laplacian encoding. There are a few different types. And actually, the very well-known paper that does this is benchmarking graph neural networks. They basically enhanced a lot of different graph neural networks using this topological information, and they show this basically always improves the results. So it's a very nice thing. It's very simple, very powerful, cheap computationally. Basically, very little reason not to do this. So this is also the simplest way to incorporate topological descriptors. You can use them as whole graph features. This is especially useful in chemistry, where those descriptors can be very global in reach. You have a lot of different descriptors that are very proven to be very useful. So we compute the descriptors for the whole graph. For example, Wiener index is naturally for the whole graph. And we concatenate them with graph vector after the convolutional layers, after this readout, and before the MLP. So you compute those convolutions, then you have the readout, and the readout gives you the vector for the whole graph. And you just concatenate to these vectors additional features based on graph topology. You just have the longer vector, and then you put it into MLP. You can backpropagate with no problem. And this has been introduced, for example, in paper Analyzing Learned Molecular Representation for Property Prediction. This is a quite interesting and very powerful graph neural network, but even this powerful network can be improved by adding topological features. Authors show that it's, in general, a very good idea. This is very beneficial, especially if you use more global topological features, because graph neural networks, due to this message passing, and message passing is very local, so you pass messages between the neighbors. So graph neural networks actually have a problem with learning long-range representations, long-range features. This is quite problematic in chemistry, where we have large substructures, and they are pretty important, like functional groups. So this is very, very useful in those cases, if you choose those descriptors well. And we can also use graph transformers, because of course you can use transformers. And the idea is as follows. So attention, at its heart, on any object is learning on sets. Attention is set learning because it ignores any ordering or structure of the input. Attention, as a mechanism for weighting things, is everything to everything. For texts, every word attends to every word. For images, for image transformers, every image patch attends to every image patch. There is no notion of order at all. It's naturally permutation variant, of course, for this reason. So it's sounds pretty important for graphs where everything has to be permutation variant. But transformers, for text, for images, they inject this structural information via positional encoding. For example, word order in text transformers is implicitly taken into consideration by using positional encoding. You have the same for basically every structure, because it's not like we are only learning on sets, right? We don't have a set of nodes in a graph. We have a graph structure. So we have to, and we also have the correct order of words in a sentence. So we have to incorporate not only attention, but some positional encoding to encode the structure of what we are doing. So to use this on graphs, we actually use topological descriptors, because of course we do. Because every node attends to every node. The idea is exactly like set learning. This is basically like using a full graph where everything is connected to everything. Yeah, this is not scalable, by the way, for this reason. But every node will attend to every other node. But this ignores the graph structure, right? Totally. We throw away whatever, for example, the chemical molecule looked like. But we encode it instead using topological descriptors, because topological descriptors describe the topology very well. Graph transformers, for this reason, are based on topological descriptors. You cannot have graph transformer that does not use topological descriptors, because simply it wouldn't work. For example, in this paper, which introduced the graphomer paper, this is the image on the right, this uses centrality, very simple to what we talked about, and shortest paths, because those are obvious to descriptors. And this combines node features with centrality values and shortest paths via edges. And combines these topological descriptors, which are extremely simple, with attention on nodes and the typical transformer. And this actually got a very good publication at Neural IPS. This really got the first place on many benchmarks, despite this being a very, very simple idea. So this is graph transformers, all use topological descriptors. This is the third way to incorporate topological descriptors to GNNs. So this is the end of the presentation, and I'm happy to take any questions if you have them. If we don't have time or you think of the question later, you can write me at this university email. I will be happy to answer.
Thank you for this great presentation. I think we should put some claps. For me, it was really interesting, and I have learned a lot of things. But maybe before I start asking my questions, maybe there are questions from the audience.
Actually, I would have one. That was a pretty simple question, mostly because I'm not familiar with the topic so much. But let's assume that we have a graph that vertices hypothetically have the strength associated with them. Would it change the way of analyzing such a graph in some more sophisticated way than simply making some ghost hops that you are simply making 9 hops instead of 1 hop? Or something like that?
Could you elaborate on this? What do nodes have?
Strength, connection strengths in some sort.
So you mean some weights to the edges?
Yes, basically.
So adding weights to edges is basically adding the numerical descriptor to an edge. This is pretty natural. This is, for example, very natural in traffic networks. In traffic networks, you have the capacity of a road. So this is basically or length of an edge, indeed, because in roads, of course, we have the length of the road, right? So we can incorporate this. For example, graph neural networks can very easily incorporate weights of edges in message passing because message can be weighted. Additionally, if this is critically important, so for example, you are very much focused on edges, there are techniques that focus more on edges than on the nodes. For example, in this paper for molecular property prediction, actually they thought that edges are more important for molecules in this case than nodes. So they did basically something like message passing between edges, and they focused on those edge attributes, including some edge strength in a way.
So it's a simple descriptor and can be aggregated.
Yeah, it can be aggregated, can be incorporated. Yes.
Thank you.
There was a question here.
Hi, thank you for your great presentation. Actually, I had a similar question. What about weighted and directed graphs? Because in my master, I deal with brain connectivity networks, which are directed and weighted, and I wanted to ask if you have any experience with those.
Yeah. So if we go here into this adjacency matrix, a directed graph is basically a graph where this is not symmetric, right? And weighted graph is basically here this adjacency matrix where those edges don't have ones but some weights, right? So this is actually pretty problematic for graph neural networks because if this is not symmetric, this actually does lose quite a few nice properties mathematically. For example, you can't do easily eigen decomposition of this. You can do eigen decomposition, but you are not guaranteed a few useful things. And there are graph neural networks that are made for this, but you can't use just off-the-shelf graph neural network. This is important. You can just take any network because it won't work because it assumes the symmetry of this. So you can use graph neural networks, but you have to search for relational graph neural networks or explicitly something for directed message passing. This can be done, but yeah, this is much more problematic. Topological descriptors can be used because topological descriptors often have definitions for in degree and out degree, which are used for indirected networks. So for graph neural networks can be problematic. For topological descriptors, they can be calculated. You just have to search if it can be used in this situation.
Okay, thank you. And this LDP method, how does it deal with?
This was made for undirected graphs, but actually this LDP method actually would work also because in LDP you calculate vertex degree and statistics of neighbors' degrees, right? In directed graphs, what happens? You have in degree, so that the number of edges towards you, and the out degree, so the number of edges from you. So you could, for example, you could calculate average degree for a node. Or you could calculate, for example, 10 features. So those 5 features for in degree and another 5 features for out degree. And you would have just 10 features and this would also work.
Okay.
Something like that.
Okay, thanks.
It's great there are questions.
Okay, so thanks for the presentation. And I have one question about the histograms.
Yeah.
So they are used like as an aggregation function. Does that mean that there's like some neighborhood that is like averaged to take like, because if I understand it correctly, there's like this histogram is a single value. And
the histogram is okay. So this works like this: you compute those 5 features for each node, right? So you have 5 columns and as many rows in a matrix as there are nodes in the graph, right? So for each of the columns, you take the column, so the set of values of the same length as the number of nodes, and you calculate the histogram of those values. So for example, if there are 30 nodes in the graph, you will calculate the histogram of 30 values of this column. So you take a histogram of each column, so you take 5 histograms, and you take those 5 histograms. Each histogram is basically a vector, right, of values, and you concatenate those vectors. So histogram has the constant length. It's computed from the column values.
okay, thank you.
Are there more questions? Okay, so I have a question regarding the simplicity of some of the features, especially the shortest path. What is the computational complexity of calculating the shortest path? I mean, you use some kind of a dynamic algorithm for that, I guess.
Yeah, so actually, for example, edge between centrality computes the fraction of shortest paths for each edge, right? So you have to obviously compute shortest path, right? So actually, there are optimized algorithms that can compute this value, for example, for those centralities based on shortest paths. For example, there's algorithm called Brandes' algorithm from, I think, Ulrich Brandes, which has complexity O, number of vertices times the number of edges. Mm-hmm. So this is basically many algorithms for topological descriptors have linear complexity in either number of vertices, number of edges, or both. Mm-hmm, so they are typically very cheap.
Because the other descriptors are even simpler, right? I mean, like computationally, they're simple, but still, this is very simple. The second is just a remark about the Jakub index. Actually, I have used it many years ago in some kind of algorithm for computing the semantic similarity between pages in Wikipedia, and it also turned out to be very well working for this problem. So I guess yes, here I've seen Jakub index and I was okay. Yeah, that's a very good feature, not only in my in my research. So I think we have reached the end of the presentation. Maybe still there's some question in your mind. If not, thank you once again, Jakub, for this presentation. Claps. And don't forget to subscribe to our channel on YouTube. Thank you.